On May the 6th, we honor Dan Wertheimer and Paul Horowitz, two SETI pioneers who will be receiving the 2021 Drake Award. But before the big event, we turn to the perspectives of three previous winners of the Drake Award to chat about their work, the future, and where, or if, the discovery of life beyond Earth will actually happen. My name is Simon Steele. I'm the Senior Director of Education Outreach at the SETI Institute, and I'm very pleased to be joined by the 2019 Drake Award winner, Jason Wright. Jason is the Professor of Astronomy and Astrophysics at Penn State University and Director of the Penn State Extraterrestrial Intelligence Center. The 2018 winner at the Drake Awards, Vicki Meadows, who is Professor at the University of Washington Department of Astronomy and Director of the University of Washington Astrobiology Program. And last but not least, Bill Borucki, the 2015 winner. Bill is a space scientist who worked at NASA Ames and started his career designing heat shields for the Apollo program. He later became interested in exoplanets and was one of the driving forces behind the development of the Kepler mission, becoming the mission's principal investigator. So welcome everyone to this chat. And I think just want to start out, usually one of the first questions people get asked is, when did you first get interested in astronomy? And usually the answer is by the age of 4, but let's do a slight variation on this. When did you first get interested in searching for life in the universe? And what was your motivation to get into this field, a very special field of astronomy and astrobiology? Maybe we'll start with Bill.
Well, I got interested actually in that a little bit when I was in high school. In high school, I was president of the science club. The teacher suggested as a project that we do count droplets of water in a gallon of water. I thought that was sort of a stupid project. So I suggested that what we do instead is contact flying saucers. And what we did then was divide the group up into building a transmitter in the ultraviolet, one in the visible, one in the IR, to see if we could do that. At that time, flying saucers were very frequent. Lots of people saw them. I thought that would be a great project. Building an ultraviolet transmitter when you're in high school is quite a trick. One of the things you learn from your instructor is how to blow glass, how to cut glass, how to build vacuum systems, how to repair vacuum systems, and then you graduate. You may not have accomplished a great deal in terms of contacting flying saucers, but you certainly learned a lot of techniques in physics. When I went to NASA Ames many years later, one of the things I recognized was that it was really, really important if we were going to search for life, because you had to find out whether or not there were planets around other stars. If there were no planets, there was no life, no Star Trek, no need to think about the project any further. So the first and most important step is, do you have Earth-like planets around other stars? And so I looked into building a mission that would tell us what the frequency of Earths were around the stars. It became the Kepler program, and it taught us that most stars have planets. There are planets that are Earth-sized in the habitable zone. So that helped, I think, a little bit help us understand the Drake equation, or a factor in the Drake equation. And that's sort of been my contribution.
Okay. Vicki, how many UFOs were sighted when you were in school?
Oh, I don't know. So I went to school in Australia, where I don't think that was quite as big a thing as it was over here. But I think I became interested in the search for life elsewhere. Probably also very early on. I was a big science fiction fan, and so I read a lot of science fiction, even when I think I was in elementary school, in fact. So I've always been interested in the quest for life elsewhere. But the first opportunity I had to actually do it for real, for my living, was in the year 2000, when a call came out to join this thing called the NASA Astrobiology Institute. And a part of that, so this was a NASA proposal, a part of that was, can you use what we've learned about the Earth and about solar system planets and use that to help us try and understand what we should look for on extrasolar planets that might be able to support life or have life on them. So for the last couple of decades, I've actually been paid to actually search for extraterrestrial life.
Mm-hmm. Jason, UFOs on the East Coast.
So I definitely read science fiction as a kid, and I'm sure it was influential in, how I got into astronomy and what I wanted to study. But it never really occurred to me to look for life elsewhere in the universe. I was interested in stars like the sun and how they behave. And in my graduate work, I did look for planets around other stars, but I wasn't actually motivated by the search for life. I just thought the planets were cool. But my advisor did, in a kind of offhand way, suggest that we might do a project looking for Dyson spheres, which just blew me away. I said, what do you mean? And I mean, I'd heard of Dyson spheres, but I hadn't thought of it as something I would really do. It turned out that his suggestion, we played around with it briefly. It just wasn't going to work, and so we put it down. But then about 6 years ago, I saw a talk about a new satellite called WISE that had surveyed the sky at exactly the wavelengths you would need to do that project that had been suggested back when I was in graduate school. And I was like, wow, we could do this now. And then another colleague said, the Templeton Foundation has this call out to do stuff that you can't get money for otherwise in astronomy. And we thought it would be fun. So that day we fired off the little step 1 proposal, and then we fired off the step 2, and then we got that award, and then we did a big search, and then we had more ideas, and one thing led to another, and suddenly it's most of my research. And so it was just that I happened to get that suggestion in grad school, and I happened to see that talk.
Wow. So you've been talking, there are different approaches about what we mean by life in the universe. Obviously, Vicky has started off with the small things, and Jason, we suddenly made this leap to spheres surrounding entire stars. I suppose that this is addressing the search for life in different ways, and they're different from how Frank Drake originally began looking for technosignatures. How does your work play off of the original searches for radio signals? We're diversifying, aren't we, in the way that we're searching? Jason, how talk about Drake, maybe Frank's contributions, and how it's similar or different from yours.
Right. It was in 1959 that Cocconi and Morrison published a paper saying that radio waves would be a good way to communicate, because at that time we were just building radio transmitters and radio receivers that could communicate at interstellar distances. So it's not what they were for, but they pointed out they could do it. And that really opened people's minds. And suddenly there was this rush of ideas for how we might find intelligent life elsewhere in the universe. That same year, Frank started Project Ozma at Green Bank Observatory to do exactly that. He had a very similar idea. It was in very short order in 1960 that Freeman Dyson said, no, we should be looking for Dyson spheres. And then it was just a few years later that Charlie Towns and Schwartz had a paper saying, no, you should use lasers, because they were working on lasers. And then we had Ron Bracewell right around that time also suggesting that we should be looking for probes in the solar system. And so there were all of these different ideas for how we could look for intelligent life in the universe. And so it's always been this big, broad thing. And it was around that time that Frank wrote down his Drake equation, the Drake equation at Green Bank, which said, just like Vicky said, and Bill said, if you want to have life, there are precursors for that. Bill said, if you don't have planets, you don't have life. So that's one of the terms in the Drake equation. So that's sort of what I worked on as a graduate student. And then if you want those planets to have life, they have to have the right conditions for life. They have to be in the habitable zone. And that's what Kepler helped us with Bill's contribution. And then if they're in the habitable zone, they're going to have to get life on it. And that's what Vicky has been working on. How do we get that life? And then that last step, what's the technology that we might be able to develop? That's the stuff I've sort of worked on. And it might be very small, just one little radio transmitter, or it might be, like we said, a Dyson sphere, something that spans the whole solar system.
Yeah. So I'm going to come back to Kepler in a little bit, which is revolutionary. Vicky, what do you use as far as an instrumentation is concerned to search for life?
Okay, so my project, at the moment, we're still largely theoretical, but we're at a very, very special time when we're about to get data to actually work on this. And I thought Jason's description there was great, because if you can think of it, each of our careers for the three people you're interviewing here on the table kind of personify one step of the Drake equation, right? Mm-hmm. So what I'm interested in is, what fraction of planets actually do have life on them. So that's my term. So in our case, what we need to do is be able to study planets that are small enough to potentially have surface oceans on them. So rocky worlds, not big gassy worlds, but rocky worlds that could have oceans on them and therefore life, and at the right distance from the star that they can support an ocean. And so that's where that habitable zone concept comes in. And so to do that has been really, really challenging. But there's now this amazing system called the TRAPPIST-1 planetary system, which is a system of 7 planets orbiting around a star that's not much bigger than Jupiter. And because the host star itself is so tiny, it means that we are able to get enhanced signals from the atmospheres of these planets as they pass in front of that star. And so with the launch of the James Webb Space Telescope, which is coming right up, we hope this year, later, we will be able to take some of the very first spectra of the atmosphere of terrestrial planets orbiting around other stars. And so that begins the search to try and say, you know, can we see, first of all, do these things have an atmosphere? That's kind of important for keeping an ocean. If you have an airless world, you can't keep an ocean. So one of our first steps on this path will be, you know, do these terrestrial planets that exist around other stars, do they have atmospheres like we have atmospheres to help support an ocean? And so I'm looking forward to JWST. And then down the way, NASA has these really ambitious concepts that are currently being debated in something called the Astro 2020 Decadal Survey. But some of the concepts that are currently being considered for ranking as to which one goes first or whatever, some of these are huge telescopes that will be able to what we call directly image terrestrial sized planets around other stars. So that's, you know, Earth-sized planets around other stars. And those will allow us to, you know, we'll only see the pale blue dot, that beautiful pale blue dot that Sagan, you know, promoted from the Voyager spacecraft. We'll see that. We won't be able to see any detail on it, but we will be able to get spectra of those planets and potentially tell whether or not they have atmospheres and oceans and so on. So there's an arc of telescopes that are coming that are going to help us measure the atmospheres and potentially surface conditions of terrestrial planets. And so we will be able to get a much better idea of whether other planets out there can support life and whether or not they even have life on them.
Yeah. And in a way, the Kepler mission started it all. It sort of reinvigorated this whole concept of planets being everywhere. Bill, can you say a little bit about the legacy of Kepler and maybe where we're heading, or where you would like to see us heading post-Kepler?
Well, certainly what Vicki said is really important. We want to build these big telescopes. We will use them to get spectra of the atmospheres that will tell us, do they have water? Are there special molecules that might indicate the presence or probability of life? So that's really an important direction. When in the early 80s, I started coming up with the idea of a Kepler mission and the equipment necessary to find tiny planets. One of the things I recognized was it was a very different direction than Frank Drake's direction. Frank Drake basically is playing golf for a hole-in-one. If he's successful, if that approach is successful, we don't need any of these other techniques. We can ask them, you know, what's going on in your planet? What kind of life do you have? Do you have microbial life and dinosaurs, whatever? But if that isn't successful for some reason, our method of doing one step at a time, finding if there are planets, finding out what kind of atmospheres they have, finding out if there's life on those planets, building bigger telescopes and more comprehensive techniques to find out about that life is another approach. So there are two parallel approaches to the search for life in our universe. And it will be interesting to see which of the two works first. Both of them are difficult, but I'm really delighted to see there are two completely parallel and different approaches.
So I'm interested, when did you first hear about Frank Drake? Let's start off with going back to Vicki in the bottom right-hand corner for me. Of course, Frank is such an icon in this field. Did you learn about the Drake equation in college, or was this something that came up randomly?
Yeah, I think I might have actually learned about the Drake equation at uni for me, but I think certainly the Cosmos series brought that to my attention very early on. So I think Carl Sagan's Cosmos really opened up that and introduced me to Frank Drake in the process, and so that was really the beginning for me.
Yeah, Jason.
I don't actually remember when I first saw the Drake equation. I presume I must have come across it in my readings in high school, say, or college. Interestingly, I never actually saw Cosmos or read Carl Sagan. He wasn't actually a big influence on me. I mean, I love Carl Sagan, and I've read the book since then. But so that would not have been where I've heard it, but I actually don't remember.
Yeah, okay. And Bill, I just intrigued.
The announcement, of course, was 1960. That Project Ozma. I had made measurements, I think, of 3 stars, Epsilon Eridani, and a couple of other stars. I heard about it right away. I subscribed to Sky and Telescope and all these other astronomy magazines, and they carried information about that. So I heard about it right from the beginning, and I thought that was an absolutely wonderful way of phrasing the difficulty of the situation and all the factors that go into trying to find extraterrestrial life. And the fact that he was able to do this with present day equipment was wonderful, because up to then people had no way of making a contact. So it was just a wonderful announcement that it had been done, and that it could be done even better in the coming years.
Do you think that the equation is still relevant? The SETI Institute obviously displays it proudly in its foyer. Is this a roadmap? Obviously, there was a thought experiment back in the 60s. Is this still relevant, or are we missing something in terms of the search?
It's quite relevant. Basically, it's a way of describing all the different factors that basically influence how much life there is in the galaxy. If you don't have any civilizations, zero. All the different factors. You have to have planets, you have civilizations, you have to have atmospheres. It's a nice way of writing down the complexity that's involved in extraterrestrial intelligent life. I don't think we can measure all these things, but conceptually, it helps us understand the situation in a beautiful, succinct fashion.
Any controversial views from the other two?
Many people, the Drake equation, Bill is exactly right. I think Jill Tarter likes to say that it's a great way to parameterize our ignorance. And the terms in that equation track maybe the units you would have, for instance, in an undergraduate life in the universe course. First, you learn about the astronomy and the stars, and then the planets, and then you learn about habitable zones, and then you learn about how life formed, and then you learn about how life evolves. I mean, it's just, it captures the whole problem of astrobiology. And so it's really been a wonderful guide. Many people over the years have suggested tweaks to try and incorporate more details, modifications of it. I think the biggest modification that might be relevant is that, unlike microbial life, as far as we know, is that technological life can spread. And so what the equation tells you is how many technological civilizations might be on the planets where they arose. But for instance, it totally misses Mars, which has radio signals coming off of it and technosignatures because we put them there, but never, well, as far as we may have hosted life, but did not need to host life originally for that to have happened. And so in humanity's future, it's entirely possible that we will spread not only throughout the solar system, but give us long enough, like 1 million years or something, and we may even spread to other stars. And so it's possible that the number of sites of technology in the galaxy is actually much larger than the number of sites where life originally arose. And that isn't accounted for in the equation very naturally. But I don't think that detracts from it. I think every time someone says, the Drake equation doesn't account for this little element, it's showing us how powerful the equation was to get us thinking about these things in the first place.
Yeah, I think, each term really encapsulates an entire field. And so it is extremely broad. But I would agree with Bill's earlier point too, if I can be slightly controversial, is that if you want to search for life in the universe, you don't have to go through all of the terms of the Drake equation, because we've now shown that we can go after microbial impact on an environment. So even if your civilization or your microbes don't evolve to build a radio telescope, we still now think we have a chance of being able to detect them. And I'm not sure that was really apparent when the Drake equation was written. So the Drake equation went and said, okay, if we're going to detect this life in the universe, it has to be able to, talk to us. But in this case, we can go after things that are completely silent. but that impact their environment, in very measurable ways. So there's kind of maybe a potential bifurcation and a little bit of an exit ramp there if we want to look for simpler forms of life from the Drake equation. But certainly for the search for extraterrestrial intelligence, absolutely, the Drake equation is still very relevant.
What about, let's just talk a little bit about close to home. Obviously, we're exploring Mars now and have been for a while looking for life. And there's Europa Clipper coming up to start exploring one of several ocean moons in our solar system. We also had the wonderful thing that we're not going to mention too much is Oumuamua, where we've got potentially an alien artifact in our solar system, but potentially not. And I'm willing to drop that very, very quickly, that topic. But, as far as the solar system is concerned, what sort of things do you think we can possibly discover without even leaving the confines of our sun?
One of the most important things by far is, do we find life on any of those possibilities, on Mars or Europa or something? If the answer is we do find life, that really indicates there's probably a lot of life in the galaxy. If on the other hand, we find none at all, that's a bit scary. After all, Project Ozma was in 1960. That was 60 years ago. We still haven't picked up any signals. We like to make the assumption that, there's billions of planets that are habitable planets around other stars. What's the actual value, the probability that if the conditions are right for life, it actually starts? The answer might be 0 or pretty close to 0. We are the one outlier. So understanding whether we have life on our own solar system somewhere is going to have a big impact on our ideas about life in the entire galaxy.
Vicky, do you have hopes for Mars or Europa or Enceladus?
Yeah. So I mean, I've actually organized public debates where it's like, will we find life in the solar system first or on exoplanets? And so I can talk about the pros and cons of each.
And I'm going to ask you guys that as well in the next question.
So I think what's really interesting about the solar system is I think it gives us a chance to go and search in relatively inhospitable environments, again, to test Bill's point here. Can life arise in a variety of different environments, right? And so we can go look for that. And the advantage of in the solar system is we can get there, we can have multiple measurements and be in situ and actually touch stuff. Which is really fantastic. And so it gives us a chance of potentially working through sort of the search for life in a relatively information-rich type of environment where we're able to send spacecraft with lots and lots of different measurements, for example. But I will say that the life there is going to be in very challenging or specific niches. I mean, we're really talking about fairly extreme environments, even though some of them may indeed be habitable, like the subsurface of, the subsurface ocean in Europa, subsurface of Mars may also have liquid water in it. But the great thing about exoplanets, and actually you've got a stacked deck here because you have all exoplanet scientists here, right? So
I know.
The great thing about exoplanets is that what we're looking for in exoplanets is sort of a global modification of the environment by life. So that's our definition of an exoplanet biosignature. And in that case, you're talking about trying to find a system that is squelching with life, that has abundant life everywhere. And so even though the measurements themselves are difficult, the signal is much larger. And so there's kind of a trade-off in, can we go to a place where, life certainly isn't apparent just looking at it, but, can we get down there and study it versus, okay, I'm now going to try and find, a global biosphere on another planet, which is just sitting out there on the surface, interacting with the atmosphere, waving at us, So I think there's a trade-off in that. But I would go for Team Exoplanet and say, I think it might be easier to look for places where there's just habitability and a biosphere everywhere. And then that might not be as challenging as some people might imagine.
Because if we find fossil life on Mars or life in the oceans of Europa, those are two, you're not going to discover that in another planetary system, are you? Because it's so subtle that we can roll over it or, land on it, and it's still difficult to make that call. So that stuff is not going to be found outside our solar system. Yeah.
So it's the difference between abundant surface life and life in niches under the surface. So very different technique, you know, and I would love to find life in the subsurface in Europa and Enceladus, Mars. That would be fantastic. But yeah, it's not something we're going to be looking for in exoplanets. But exoplanets have the advantage that we don't just have, you know, our suite of planets here. We have potentially, you know, at least with some of these larger mission concepts, up to 30 planets we could study in detail that might be habitable. And so we get a larger statistical chance, plus also potentially a larger signal because we're looking for biosphere that's colonized the entire planet.
Yeah, yeah. But an independent life form on Europa suddenly changes the statistics, doesn't it?
Absolutely.
Yeah.
That would be.
It would be an interesting question. I'm sorry.
No,
Go ahead.
go ahead.
I'd say it would be an interesting question, you know, how we know that it's independent, especially if it seems to share a lot of Earth characteristics. You know, could there be a common origin? Does all life happen the same way? Just so many things you can learn if you find it here in the solar system that will be very challenging to do on an exoplanet. But I definitely agree with Vicky. I think it's great to think about the solar system and how far we've come. I mean, at the beginning of the 20th century, it was, at least in some scientific circles, a perfectly reputable thing to talk about the civilizations on Mars. I mean, people were mapping the cities and the canals and things like that. And it was controversial, but it was definitely in bounds for scientific exploration. And in fact, some of the maps, for instance, made by Slipher of canals and things, were used in planning the Mariner missions to go actually take pictures of Mars and see what it was really like there. And so the people on the Mariner missions would have grown up hearing these stories about cities on Mars and so on. And so very quickly with the Mariner missions, we went from maybe cities to Mars is basically a desert. And things swung really hard. And since then, it just hasn't seemed likely that there'd be any obvious life and definitely no obvious technology in the solar system. But I think that things swung so far that we've stopped even wondering or looking for it. And the Oumuamua thing you brought up, okay, disclaimer, there's no reason Oumuamua is alien spacecraft. It's not, it's a comet. Yep. or iceberg or something like that. On the other hand, I think it has restarted this conversation of, you know, how do we know there's nothing there? So I'm looking forward to actually saying things like, we're sure there aren't alien artifacts or, you know, technology on Mars because we've checked and looked, and actually, you know, saying that we know that instead of just saying, oh, well, you know, we would have noticed. And you know, because as scientists, we want data. And so I think there's also a lot of SETI to do in the solar system in that sense of quantifying, which seems obvious to us. You know, that there doesn't seem to be anyone here.
Yeah, I think as you're right, it allows you to start considering things that maybe were not on the table a while back. And maybe just an ask, how do you see, you know, the search for life of any form, whether it's technosignatures or biosignatures, how would you push the envelope on these searches? I mean, if you maybe not limited by budget, or even just slightly moving aside from, you know, the usual suspects of habitable zone planets, where would you like to push this slightly to the controversial edge? And I'll let anyone start.
I'd like very much to see SETI develop a system of detecting signals for neutrino fluxes. Now, SETI was based on the idea that at certain radio frequencies, there's very little interference from the cosmos, and you can transmit signals a long distance for very little power, very little expense. Neutrinos, again, flood the universe as well, and you produce them with nuclear reactors and all sorts of things. You can't detect them very well today, and so if they were modulated and flowing through the whole galaxy, so, you know, and communicating that way, we couldn't detect that. But we should be able to design detectors that would allow us to pick up signals, you know, for the polarization of neutrinos or their entanglement, all sorts of properties these neutrino flux might have. So I'd like to see some effort, some development in the ability to look at neutrino fluxes for modulated signals.
Okay, Vicky, you're up.
Okay, well, I'll be the conservative on this panel. I will say I still want us to look for biosignatures, but if I had no budget, I mean, no limit on my budget. What I would like is, you know, we currently have a lot of things in sort of the pipelines that may potentially be ranked first to go. Things like the LUVOIR mission that are this, you know, potentially a 15-meter telescope in space to allow us to directly image these planets and so on. But I remember back when I was a tiny scientist, we were also talking about something called TPFI, the Terrestrial Planet Finder Interferometer. And this is a super ambitious thing where we're actually flying multiple spacecraft in space that have precision flying and allow us to do interferometry in the mid-infrared. And the mid-infrared is valuable because that's kind of a window in the Earth's atmosphere where our radiation escapes to space when we let it, if we don't build up our CO2. And in that window, you know, we can learn about the temperature of the planet. We can learn about a lot more molecules. So I would try and push us out into a much broader wavelength range than we currently have planned. So my dream thing would be, you know, initial reconnaissance from JWST, and then, you know, some kind of large direct imaging capability, probably visible to near infrared, UV, whatever. And then beyond that, I think we want to also be able to get that information in the mid-infrared as well to complement what we're getting in the visible and near infrared. So it allows us to really check on conditions like potentially surface temperature and just allow us to get a much wider spread of not just biosignatures, but also the environmental context that we need to interpret what we're looking at. And so, yeah, so if I had all the money in the world, I would want to build this formation flying near infrared.
And I think Vicky has another suggestion, has another wonderful factor, and that is it's expandable. You can have a lot of mirrors, you can have a lot of the system put together, and so you get very high resolution, much beyond anything else. And so you might be actually able to look at the surface of the planet and say, oh, there's chlorophyll there, and there's not in this desert area. It can expand into the future, and the technology can grow and give us much more valuable information along that development line. So it's a great idea.
There's still decades and decades of telescope development ahead of us in this area. It's certainly not.
Live a long time.
Yeah.
Jason, what do you want to do?
I really like both of those ideas. I love space interferometers and infrared and the optical. And I've often said that, you know, if you really want to go looking for something like Dyson spheres or ruling out that they exist, even at a very low level, then we need to go to the mid and far infrared in space and do sensitive surveys at high resolution. So I'd want a very large infrared telescope of like 100 microns. And you would do a lot of amazing science if you could look at the entire sky and map it at high resolution and high sensitivity at those wavelengths, get spectra. That would be great. But I'm actually going to dodge your question a little because I think SETI is a bit at an unfair advantage here compared to the rest of astrobiology. Because of the work of the NASA Astrobiology Institutes and people like Vicky, we've had decades of time to say, to answer NASA's question. Like, you know, if we were going to launch a $10 billion mission and we were going to make finding life in the universe one of its priorities, what would the instrumentation need to be? What's the best chance we're going to have? And so for a long time now, we've had lots of very smart people working very hard to give NASA a very good answer to that question, all the way from what would we look for, to how would we look for it, to how would we be sure that we've found it, what are all the false positives? That's a big topic. And SETI, in a lot of ways, is just getting started. Very few people work on this. There's only a handful of people that have PhDs directly related to it, like fewer than 10. And so if I had an unlimited budget, what I would actually do is go back to where astrobiology started and start building up a curriculum and start building up degrees and start building up a lot of these just brilliant young people coming up through the ranks of astronomy to answer that question. And so I would say, you know, give me a little bit of the money now to set that up and then give them the money in 20 years because they'll have a much better answer than I do right
now. The other thing, though, people have talked about is you'd like to build a really good radio telescope, one that covered Australia, for example. Now you can listen.
That's right.
You might be able to pick up the signals from the radio stations or radar stations from other civilizations. And it sounds impractical until you realize you're not covering it all with a dish, wire structures that would allow life under it. So it's not impossible. And similarly, you know, we want to go to the moon, we want to build colonies there, we want to expand into our solar system. Let's put a big radio telescope that would cover, you know, 1,000 square miles or 10,000 square miles on the backside of the moon where there was less interference. So I think there's a number of technologies that we could use if we had the money to go ahead and build them.
Yeah, that's a really good point. The Square Kilometer Array is a proposed telescope network that's starting to be built now. And if it gets completed, then it should be approximately sensitive enough that it would be able to detect not our deliberate transmissions, but our just passive leaked transmissions from another star. That is, if there were a twin of Earth with all of our aircraft radar and all of our TV stations and radio stations at Alpha Centauri, the square kilometer array would in principle be sensitive enough to pick that up. And that's a game changer, because then you don't have to say, oh, they're trying to transmit to us. You can just say they're there and they use radio waves, and we'll be able to detect them.
In a sense, Jason anticipated one of my last questions as we're coming up to time. And that is getting the next generation of humans invested in this search. You know, searching for life in the universe is acceptable. Even searching for intelligent life is becoming acceptable. You know, acceptable to mainstream science. What would you tell, you know, the next generation? What have you told the next generation of researchers or kids still in school about why you should follow in this footsteps, to attend Jason's Academy of SETI, you know, the Starfleet or whatever? You know, what is the purpose of this? There's lots of other things to do, but why is this exciting, and why is it going to get more exciting?
How can you miss? You know, if you're a grad student, you want to accomplish something worthwhile, you've got the intelligence, the curiosity to get your advanced degrees, you have a chance to place humankind in context with life and intelligence in the entire universe. God, that would attract anybody and everybody above the intelligence of a worm.
Okay, Vicky, follow that one.
All right. So as you said, I'm the director of the astrobiology program at the University of Washington. So we're actually walking the walk. So we train graduate students to be, and I think this is key, interdisciplinary researchers. And so I think one of the advantages of also the search for life is it's really one of those big questions. It's the biggest question. Are we alone? Are we alone in the universe? And I think because of that, you need to do a form of science that hasn't always been mainstream, which is this very strongly interdisciplinary science where you bring your expertise to the table, but agree to work, you know, with a team of exceptional scientists to bring all of your expertise to bear on questions that are so large that a single discipline can't answer them. And so, you know, I think the search for life is definitely that type of science. And I love that type of science. I love learning from my colleagues and again, just going beyond what you are capable of into what this, you know, the super team is capable of. And so I think that's just super exciting. Plus, I think interdisciplinary science is really kind of where we can really expand the power of science going forward. And so training someone to be an interdisciplinary scientist is just valuable for science all around, not just, you know, answering these big types of questions. So yeah, if you love learning about all sorts of different science, you know, this is the field for you.
All right. You know, I like to say that I'm lucky I work on a problem where I don't, you know, if someone asks me what I do and I say I'm a scientist, they say, oh, what do you study? When I give them the answer, you know, their eyes don't glaze over. I don't have to like get all technical. I just tell them what I do and they're like, wow. Like, and you know, it's not most people don't get that reaction when they tell them about what little corner of science they work on. And so I don't think it needs any salesmanship. I agree with Bill and Vicky that it's just people understand that this is a big problem. I have found that most people just simply don't know how they can contribute, or they might suspect that it's not a very serious science and that you know, it's not developed enough to be a meaty problem that we can really work on, or it's based on too many assumptions. And so I think that if I want to convince them that this is something to do, I need to be able to, you know, credibly tell them that this is something serious scientists are working on. We're being rigorous about this, but also that there's a career in it. That's frankly the reason most people don't get into it, is because there aren't jobs in it. I think that's starting to change. NASA has changed its tune. It has started to award grants to outside investigators thinking about the problem. I think it's getting a lot of credibility back. And so for the first time, when a student tells me, I want to do this for my PhD, you know, we don't have to have the talk about whether this is a good idea and make sure they know what they're getting into. We can just talk about, you know, the realistic options. And now, yeah, I'm happy to accept new grad students and give them study projects all the time. So I'm really hopeful for the future.
I think Jason got a good point, though. You really want to help students recognize that being a philosophy major and trying to understand whether there's life in the universe is not what we're talking about. We're talking about some abilities, something you can bring to the team, like Vicky mentioned. Are you really good at electronics? Are you good at designing spacecraft? You know, come up with the skill set that's required to participate in this exploration. It's not going to be done by one person. It's done by big teams. And so you do need to bring a strong background and skill set to participate.
So it's a team effort. You bring in skills from very many different disciplines, and it's also a global quest, if you like. This is something that is important for all humanity and all cultures, and hopefully, you know, the next generation will be the first generation to see a discovery made wherever that is. And I want to thank everybody for joining this conversation. I won't ask you to plug in a value of n unless you're willing to diverge what you would like to put into that number. But I'd like to thank the three of you, Vicky, Bill, and Jason, for joining this conversation. We're all going to be attending this year's Drake Awards and enjoying hearing about the work of the recipients this year. So thank you all very much, and I will say goodbye from the SETI Institute now.